Very good morning, all the participants. So today we are in third day, day 3 in AICTE ATAL sponsored Faculty Development Program on Electric Vehicles 2.0 Emerging Innovations and Trends in the Indian Context. In this, if we consider electric vehicle, the heart of the electric vehicle is power electronic components. If we are observe any drivetrain, because of power electronic evaluation, the more new trends or new technologies are coming to picture. So it is very important to discuss power electronic component. So today's session we scheduled in this way. Morning 9:30 to 12 p.m. Dr. Ravikiran, lead of special projects and R&D projects, Ador Powertron Limited, Pune. Topic: role of power electronics in EV applications. Later continue 12 to 1 p.m. Dr. Sridhar, yes, Associate Professor MSRIT. He will involve in article discussion, followed by lunch. Later in the afternoon session we have 2 to 3:30 p.m. we have development of embedded controllers for power converters using model based system design tools. Later a small break. It will continue from 3:30 to 4:30 with the same resource person, same topic, like development of embedded controllers for power converters using model based system design tools. Followed by, at the end of the day, we will have hands-on session from 4:30 p.m. to 5:30 p.m. Handled by Dr. Kodishwar Kumaranji, and the topic is development of embedded controllers for power converters. So we will discuss the, like you may have hands-on on converters, like when taking the sessions, he will address what are the required things and all. Now I would like to call Dr. B.V. Sumangala ma'am for inviting today's resource person. Please, ma'am.
Good morning, everybody.
Good morning.
So nice to see you all fresh in the morning. Okay, it's my pleasure to introduce today's speaker, Dr. Ravikiran Hiremath. He is currently a lead of special projects and R&D projects at Ador Powertron Limited, Pune, Maharashtra. Previously, he served as an assistant manager at Kalyani Powertrain Limited, KPTL, Pune. He carried out a number of fascinating EV-related projects. Moreover, he produced 2 notable Indian patents during his service in KPTL, Pune. In 2022, he completed his PhD in Electrical Engineering from National Institute of Technology, Karnataka, NITK, Surathkal, Mangalore. He produced 13 renowned scientific publications during PhD, which were focused on renewable energy applications. He received several Best Paper awards. Additionally, he earned a scholarship from MHRD during his doctoral studies. Completed both BE and MTech from VTU, Belagavi, Karnataka. Areas of expertise is electric vehicle applications, renewable energy applications, particularly solar and wind. So we are very happy to have Dr. Hiremath here. So I wish all participants will be benefited by listening to his lecture, specifically on power electronics and its applications in electric vehicles. So over to Dr. Hiremath. Please. I welcome Dr. Hiremath with a flower bouquet. Please come, sir. Thank you, and over to Dr. Hiremath.
Good morning, everyone. Good morning. Yeah. So the title is Role of Power Electronics in EV Applications. Here we can segregate the title into two parts. So we can see the power electronics and EV applications. So what is the contribution of power electronics in EV applications? So why EV applications? Electric vehicles. What is the definition of EV vehicles? So as we know, the electrification. So whatever we are replacing the combustion engine with electric motor. So that is, we will, in the simple words, we can define the electric vehicle. So power electronics. Nowadays, if you see the current market, it is mainly dependent on the power electronics. So that too, especially in EV applications. So because of that made me to give a title on this power electronics and in the EV applications. If something is useful in this one, so if you get that benefit, then that would be a benefit. That would be a great asset for me. So yeah. So my current company is ATAL Power Limited. It has 100 years of history. So if you look into the Xerox machine, so initially in India, that was made by our company only. So whatever the power electronics related company which is established, which was established in India, that is that too. So whatever the company which was worked on power electronics, that is from our company. So in our company we have 5 major departments. One is R&D, another is defense, another is traffic and clean air and hydrogen. Now we are moving into the hydrogen. So I am working in R&D department. And so previous my company is Bharat Forge. They have opened the R&D center in Keshavnagar, Pune. So there I got to I had an opportunity to work with electric vehicles. So there I have published 2 Indian patents. So this is my my current position. So these are the contents of my presentation: introduction, classification of chargers, power electronics, converter topology, design and calculations, simulation and results, practical overview of the topology. So just I kept one video.
understanding and knowledge about power electronics technology. What is the current number of registered electric vehicles? Based on the year 2020 global registration of new electric vehicles consisting of battery electric vehicles and plug-in electric vehicles, over 10 million EVs, that is electric vehicles, were registered during the pandemic globally. The largest number of EVs was registered in China with 4.5 million EVs, while in Europe about 3.2 million EVs were registered in the year 2020. The third largest number of EVs was recorded in the United States of America with 1.7 million EVs, while over 700,000 registered EVs were recorded in other regions around the world in the year 2020. The breakdown of global vehicle sales in the year 2019 and projected global vehicle sales by the year 2030 based on the class of fuel technology used in each vehicle was presented by a research expert in transportation and logistics. From the presented data, about 78% of the global vehicle sales in the year 2019 were classified as gasoline vehicles, while it is projected that 44% of the global vehicle sales in the year 2030 will be gasoline vehicles. Furthermore, about 14% of the global vehicle sales in the year 2019 were attributed to diesel vehicles, while it is projected that the global sales of diesel vehicles will decline in the year 2030 to about 4% of the global vehicle sales. Based on the advent of the green economy, the mild hybrid electric vehicle had 2% of the global vehicle sales in the year 2019. However, the global share of the mild hybrid electric vehicles sold is projected to increase to 20% in the year 2030. The same trend with the global mild hybrid electric vehicles was also observed with the hybrid electric vehicle, with 3% of the global vehicle sales in the year 2019. While the global share of the hybrid electric vehicles sold is projected to double by the year 2030. In the year 2019, only 1% of the global vehicle sales were attributed to the plug-in hybrid electric vehicle. The projected plug-in hybrid electric vehicle sales are expected to be 6% of the global vehicle sales by the year 2030. The battery electric vehicle has 2% of the global vehicle sales in the year 2019, with a projection of the vehicle sales to be 18% of the global vehicle sales in the year 2030. This projection shows that the EV 30 at 30 campaign, which aims that the global sales of EVs should reach 30% sales share by the year 2030, is on course. Thank you for watching and kindly subscribe to this channel for your weekly videos.
I paid rupees 99 for your webinar, and if like this, 1 lakh people will pay you 99 rupees. Yeah, I just kept this video to think on the electric vehicles. So that is also pushing to the introduction to the electric vehicles. So coming to the learning objective. So after the presentation, what are the objectives we will learn? So those are, what are the essential components of an EV application? How crucial is power electronics? What part of power electronics is involved in electric vehicle? Design and computation of power electronics topology. Simulation and results of the selected topology. Practical significance of power electronics in EV applications. In my presentation, so I have kept some simulation results based on the power electronics simulation. So we will learn those in this session. So coming to the introduction, as I said, the electric vehicle, we will define it as electrification. So here we can see the typically they have a range of 100 to 250 kilometers. So in the current market, we know the chargers, EV chargers. So usually what will happen? Type 1. So there are 4 types of chargers: Type 1, Type 2, Type 3, Type 4. Type 1 and Type 2 we will call it as AC chargers. Type 3 and Type 4 we will call it as DC chargers. So those things we will learn in the next slide. Yeah, this is the bar graph. So here we can see that the whatever the yellow is, it is there, that is electric vehicle auto sold. So the this purple color it is there, that is in EV percentage of sales, and this green color it is there, that is hybrid vehicle, and so this brown color it is there, that is a percentage of sales. So as you see nowadays, some of the brands they are going fast in the electric vehicles. So like Mercedes-Benz, Tata and Kia. So these are some of the top brands which we will see normally in the electric vehicle in the automotive industries. So so nowadays, because of the expensive of the electric vehicles, the manufacturers slowly they are moving towards the hybrid vehicle. Like it might be like petrol and electric vehicle, or so currently the Tata, whatever the Tata we are seeing, those are going with some other new ideas like CNG with petrol. And when I inquired with the salesperson, he told that the recently I think some 6 months, just if you consider 6 months, the most of the cars, whatever it is there, those are Tatas only they are selling out. Because of the new idea that he is making a combination of CNG and petrol. Because of that, so many people are there going towards they are buying the Tata cars. Even if you look into the villages also, most of the cars are Tata. Why? Because of this new idea that CNG with petrol. And if you look into the whatever the problems, whatever we are facing in the electric vehicle, so whatever, as per my knowledge, I am hearing the problem in electric vehicle because of the Ola. Because what the problem of Ola they are doing. So if you see the manufacturer aspect, if I am an industrialist, I am looking into the business. So how fast I can earn the money. So in that competition, the Ola is making money, but they're taking the backfire on that itself. Because if you look into the Bench and Kia, anything else, I am not seeing any problem in electric vehicles because people are buying happily. But if you look into the Ola, so most of the Ola bikes, those are getting fired. So because of that, people are getting they are taking step back to buy the electric vehicles. So because of the Ola, we are getting step back because of in the EV field. So that should not be done, because if you are a manufacturer, you have to take the consideration of all the aspects. Worst condition also you have to take. Even if you maybe your business would be grown after 1 year, but till that your product should be that much efficient. Even if it is the worst condition also it has to sustain. Then only your product will be reliable and it will be successful. So coming to the electric vehicle, we can see this onboard charger, DC charging station. Here we will see the two types, AC charging and DC charging. Here in the onboard charger, these are like AC to DC chargers. In the DC charging station, this is DC to DC. Here what is the main difference? Like AC charging means there are two types. Like type 1 and type 2 chargers will use as AC charging, and type 3 and type 4, that is mainly for DC charging. Like onboard charger is must in all electric vehicles, and this is a portable one. So if you consider this one, this is like whatever we are seeing the petrol ones here. So they are like in the fixed locations. That is the so as like that this DC charging stations are made. So also the onboard charger, it doesn't have any battery problems. So if you consider DC charging, here we have the like heating problems in the battery and all those things. So based on our battery capacity, we are moving from like AC charging and DC chargers we are using. So this is the classification of chargers, and here if you see the classification type, topology, dedicated and integrated. And input supply, as I said, this is a AC supply for AC charger and DC supply for DC chargers. Direction of power flow, unidirectional and bidirectional. Output power level, based on the output power level, we have made a classification, level 1, level 2 and level 3. So here you can see that level 1, this is AC, these type 1 and type 2, these are AC chargers. The maximum power rating is 1.9 kW for level 1, which is a single phase, and level 2 is a single phase as well as the 3 phase. Here you can see the maximum power is 19.2 kW. So in the level 3 we have DC charger which has the maximum capacity of 40 to 150 kilowatt, and one more charger we have, that is Tesla charger. We will see in the next phase. And in our company we have chargers which are made from bench and the charger. So there in our company we have almost like type 3 chargers. This one DC charging only we have. Like it is like 60 kilowatt, 180 kilowatt and 80 kilowatt. So these are the 3 chargers we have in our company, and we can see normally Bench and Kia and Tata, they are coming for getting charged there. Yeah, coming to the overhead chargers, as I said, type 1, here you can see that single phase, and here these two we are using for communication purpose. So you know that communication protocols means it is like interface. That is, we will call it as an communication protocols. So in the 3 phase, this is type 2. This is here we can use it as single phase also and 3 phase also. And these are DC chargers. And this is a Tesla is a this is different charger. This is only made for the Tesla cars. Here we have this in the Tesla. We have a option like whoever the owner is there, he can make a selection. That is, there are 2 options like S or X. Based on the car, they have to select S or X, and he has to get charged through this Tesla charger. Coming to the charger protection, if we are using the chargers, like we have to think on protection also, because basically in India we have IP44 and IP67 chargers normally. IP44 we will use in drier and cold closed shelter areas, and IP67 it is waterproof. Here you can use it in like Bombay side or Mangalore side. There we will see so much moist and all those things. There you can use this IP67. Coming to the so in the charger, what I can say that in the charger we have AC charging and DC charging. AC charging means nothing but AC to DC, and DC charging means DC to DC. So the thing is AC to DC, the whatever the conversion we are seeing, that is power electronics. So again we are going into the power electronics devices and power electronics topologies, and we are making the improvement there. So whatever if you look into this, if you take any of the articles, or if you go into any of the industries, or if you ask any designer, so the current trend is going with the phase shift full bridge converter. It is nothing but a DC to DC topology, which we will see in the power electronics. So why phase shift full bridge converter? So if my input supply is almost, it is in the range of 400 to 800, I want 24 volt, or output I want 12 volt to charge my battery. So if we check with buck converter, boost converter, whatever the topologies we have, like buck boost, forward converter, push pull converter, whatever the things you take, but the only problem is efficiency, and also whatever the power electronics semiconductor devices are there, like IGBT, MOSFET, whatever you are taking, it is getting blown off. So nowadays the other trend is, initially we are thinking of silicon semiconductor devices. So as the days goes on, we are moving to silicon carbide, and now we are coming to GaN, gallium devices. So what is why we are moving to the gallium or silicon carbide? The only thing is, silicon, it has less efficiency, and because as a customer I need full efficiency and I need reliability. But if I use the silicon devices in my power electronics, I don't get that much efficiency. So because of that, so much inventions made, and they are moving towards the silicon carbide. As we will accept that silicon carbide is expensive, but it will give you the high efficiency, and also it will work in the worst condition. Even it is a more heat is there, or if you are keeping your product to up to 8 hours or 24 hours also, it has that capacity to withdraw the heat. So because of that, we are making the effort to move to the silicon carbide or gallium semiconductor devices. So here in the phase shift full bridge converter, this is a basically isolated converters. Here in the input side, you will see that in the next slide what is the topology of this. So because of what is the advantage of this phase shift full bridge converter? So this is a capable of soft switching. Again, soft switching means, you know, normally buck boost we don't have the soft switching. We have hard switching there. What is hard switching and what is soft switching? Zero voltage switching and zero current switching. Both we will call it as a soft switching. In the if you take ZVS like zero voltage switching and zero current switching, in that one which is better, and why we are going for soft switching? Those things we will discuss in the next slide. So here, if you see the phase shift full bridge converter, it handles high input voltages, large output currents, and minimum stress on the power switches. Power switches is nothing but like as I said, IGBTs, MOSFETs. Those are the power switches. The benefits of this phase shift full bridge converter with phase shift control are excellent efficiency at high operating frequencies. If you go from like 1 kHz to 100 kHz, or if you go to 200 kHz, 300 kHz also, it is efficient. So, and decreases switching losses. Even the switching losses are less in this one phase shift full bridge converter. And minimal EMI and stress. Yeah, minimal EMI. So we will have the very less stress on the power switches. Because of that, we are going into the phase shift full bridge converter. And if you compare the phase shift full bridge converter with the whatever the competitor to this converter is, one more is double-ended forward converter. So there we have less capacity. There we have we can manage with less capacity. Here we will go to the higher capacity. For example, if you go to 30 kilowatt, if you go to 3 kilowatt, we will use the this phase shift full bridge converter. If you are going, if you are saying me to work on 400 watt, 350 watt, something else, then I will go for the double-ended double-ended forward converters. So this is a topology. This is a phase shift full bridge converter. Here you can see this. This will act as like an inverter, and here we will see the half bridge rectifier. Here we have the here we have the transformer. So what is the this might be IGBT or MOSFET based on the frequency. When we go for the IGBT, when we go for the MOSFETs. So if I have the less frequency, like up to 20-25 kHz, I will select IGBT. So if I go to higher frequencies, up to 100 kHz, from 40 kHz to 100 kHz and more than that, I will select the MOSFET. So this is the shim inductor, and this is the transformer. This is a linear transformer, and these two are the diodes, power diodes, spotty diodes we will call it as. And this is the output inductor, capacitor, resistor. So then the question comes: how we will select the power switches, inductor, transformer, spotty diodes, and capacitor and resistor? If we think, so this is the theoretical. If you look into the practical side, so based on our voltage rating, current rating, we will keep the safety factor as 1.25 or 1.5 based on the cost. So based on that, we will select the IGBT and MOSFETs. So we will have the calculations as per the theoretically, and based on that we will decide. So my how much is my voltage rating, how much is my current rating, and can I keep 1.5 as a safety factor, or can I keep 1.25 as my safety factor? So if I keep my safety factor at 1.25 or 1.5, for example, if my voltage is 50 volt, so I have to select my switches on the basis of 50 volt? No, because as if I want to make my product reliable, if I make my product as efficient, so then I have to select my switches into 1.5. 50 into 1.5 is my maximum selection for the switches. So how I can decide that whether my safety factor is 1.2, 1.5 is good, or 1.2 is 1.2 is good, because my whatever my budget is there, within the budget I have to select it. So if I'm keeping 1.25 as my safety factor, I have to search it present. So for the eligibility, what is the cost of this? What is the cost of this voltage in the market, and what is the cost of for 1.5 as a safety factor? What is the cost of this? So based on these things, so we will decide that. So yes, I will keep my safety factor as 1.5, and it comes in my budget, and I will go for it. So if you look into the semiconductor devices manufacturers, like if you see in the market, we have Texas Instruments, we have Infineon, we have Vishay. As a salespersons, they can come to your company and they will sell their products. Like they will tell you to, sir, take our devices, and we will give you the discount rate and all those things. So these things we can't see, like this type of practicality we can't see in the education institutes, because in the education, what is the problem here? So we will tell them to work on the whatever the formula is there, equations are there, you derive this one, you do this one. For the examination purposes, we will do it. But what is your contribution to the society? Because being an electrical person, I have to talk reality. So I know, because I have completed PhD and everything, but how much my education is giving contribution to my reality. So even I am working in industry. So normally, if you ask any industrialist, if you ask me also, we will say education, whatever you have done, derivation, whatever you have done, formulas, whatever you have bited, this one formulas, everything, you don't work in industry. Normally they will say, so whatever the formulas it is there, based on that I will get this much value, I will get this much value. That is okay. So in the reality, whether it will work or not.
But that will help for learn new things.
Which one, sir?
You are deriving equation and Maggar.
That will give you new dimension.
That
But
will
I'm
help you to learn new things, come to industry, can easy to catch up. Because of that hard work.
Yes, sir. One more thing is, what I know means, so normally the BE students' mindset is so there is always effort from the lecturers, like do good projects and get a campus. But normally, for the BE student or MTech students, if you take, they will always look into the campus, and they will always prepare for the campus. If they come on 4th year, they will always look into the campus. So, and they will leave this project, and they will look into the YouTube, and they will make it, and they will sell, and they will show us the results and everything. But at last, if they normally, what I saw, so my cousin is also there. He is in computer science department. So he is in 4th year. So I asked him, what is the project you are doing now as a computer science student? He told that something I am doing. I don't know. I am not remembering that title also. Then I told that you are attending campus also, because nowadays the campus people, they are asking mainly on their title, which project you are doing. So during my PhD journey, so lot of students, last of my juniors, when I was guiding to them, like BE projects for MTech projects, I used to hear those things. Like usually the people, they are getting hired because of their project. So nowadays what is happening, because of the big names in the college, the people, they are simply coming, and because of their target, they are taking the people. So what will happen at end the student? So normally we have our customers. For our company, we have customers from BL Bangalore, we have customers BL Mumbai, we have the customers from BARC Mumbai and L&T Talegaon and L&T Mumbai. So these are different areas. We have the customers. But so for example, we have customers from BL Bangalore. So there normally IIT, NIT people, NITs. Normally these BL and BARC, HPCL, these people will go for hiring the things. So from the customer side, so as a BL Bangalore customers, they are coming to our company, to take their product. So we are manufacturing that product. So what happened? So the same guy, so who has worked for 6 to 7 years in the same company, and recently, like 1 year back, so the one person from IIT, he got campus in the this one. He got placement in the BL Bangalore. For him, he doesn't know anything. Just he is coming to our company just to check the documentation. Even the documentation, he doesn't know anything. So the person who has worked for 6 to 7 years, he knows each and everything.
Confidential.
No, that is those are the problems, because the only theoretical knowledge it is there because of the big names the people are getting hired. So at last, if you look into the opportunity, like if you don't know anything, then the quality will remain. The quality doesn't have. So as I see, even what my suggestion is that if you are doing whole project, at least some part of the project, if you know practically also, that will boost your confidence. So that is my suggestion. Even MTech people also, when they will get into the MTech, they will always look into the placement. They don't bother about the projects also, and simply they are telling we will do this, but later they are paying somewhere and they are getting the projects done, and those things are happening here. So yeah, coming to the PSAP topology, here we have 4 switches and 2 diodes. Like this is the single phase full bridge, and this is a single phase half bridge. Here we have so many topology also. In this one, like this primary side, we can have the half bridge also. In the secondary, we can have full bridge also. So that depends on the probability we can have it. So in our topology, we have full bridge on primary side and half bridge on secondary side, which will give us the as per our application, we are getting the high efficiency from this topology. So here we have the typical topology of for power levels is more than 300 watts. Like as I said, this PSAP topology, it is for higher watts. We are using this PSAP topology, and it will give the high efficiency also. So if you look into the operation, so as I said, so here, so you know the operation here. So initially Q1 and Q2 will get turned on, and it will comes like this. This is the operation, and if you look into the secondary side, it gets triggered and it will follow this one. And during the what we can say during the adjacent Q1 and Q2, when these turn on and Q3 and Q4 turns on, then only the output power will transfer. And here you can see here, so this is the freewheeling operation is taking place here, and you can see here. So what is there? What is happening here actually? So as I said, you like soft switching. I am talking about soft switching. What is ZVS? If you see here, so 0 voltage switching I am showing you. So whenever the voltage across the switches, it is coming 0. So that time I will trigger my switches. That is called soft switching. So initially, what is happening here in the hard switching? Normally, when we are not thinking of ZVS, we are always thinking of like buck converter, boost converter. There it is. This normally this operation was happening. So here in the hard switching, you can see the voltage across the switches is about to decrease. That time we are triggering the switches. That time the losses would be more. So using the soft switching, we are getting losses less. So that is the beauty of this soft switching. So here the same concept we have applied here. So initially this Q1 and Q2 will be turned on, and this whatever the operation it is there, it will take place, and later, so here we have seen the output capacitance of the switches. It will get charged, and from here it gets discharged, and when the Q4 COSS gets discharged, then we will trigger the then we will give the gate pulse to this Q4. That is called 0 voltage switching. So So this is the, as I explained you, like hard switching and ZVS. So what is the, why we are going for zero voltage switching? Why not zero current switching? Because both are soft switching operations. Because in the zero current switching, we will see larger peak currents. In the zero voltage switching, we don't have that much larger peak currents. It is less peak currents. Because of that, we are getting less losses compared to the ZCS. So in the we are going for ZVS waveforms. Yeah. So why we are using the ZVS in PSW? So achieving ZVS in the full bridge phase shift is almost mandatory. So as I know, so in our industry, so because in my previous company also I have worked on this phase shift full bridge converter, and we have filed the 2 patents and it got granted also Indian patents. And if you go to anywhere, like any industry, nowadays it is a normal trend to say you that use the ZVS. If you are using any topology, if you are going for buck converter, they will say you use ZVS. But they don't know what is ZVS. They will tell us to do ZVS. Like, so normally, so what I will recommend the like faculties for the students, they have to look into the problem from the industry perspective, and they have to take it as their project. So if you do like that, then it will be a confidence for them to attending for the campus. Like normally in our when I was doing a PhD, so there some professors were there. Like they used to go to the company and they are asking them what is the problem you are facing. So if I am a electrical background, so if I am a good in power electronics, and I will ask the manager, or I will ask the technical head. So what is the problems you are like your colleagues are getting in terms of power electronics? So we are taking the problem from them and we are giving to the students. And some other professors are also there. They are only least bothered about these things, like what is the problem and all those things. So normally whatever I have faced in my PhD, they will tell us you have to. So they will tell us you take electric vehicle, do PhD. So when I discussed during my PhD, when I discussed with my juniors, I think almost 10 to 12 people, their guides, they suggested them to work on electric vehicle. But so PhD means we have to frame the objectives, and you have to do for the guide perspective, your objective and his objective, it should not be same, and it should have the scope. So if 10 to 12 people are working on the same field, so there might be a superposition of the objectives. So but their professors, they are telling no, we should have good objective, good scope, and we want transaction. Then only your PhD will be done. If you don't give this transaction, then your PhD will be over. And nowadays, now it is becoming a trend. Like initially they were telling that you have to get a transaction, at least 2 transactions you have to get, at least 1 transaction you have to get. Now they are making compulsory that you have to give me 1 patent. So even after the 2 transactions, if you give me 1 patent, then only your PhD will be done. Otherwise, no PhD. So these are the problems I am hearing from my juniors. During our time, we published so many good journals and we came out. But when we coming for the patents, it is very hard to get that much novelty and get it done. And that is the problem in this one. And here, so ZVS, it prevents high EMI noise, switching losses, and semiconductor failure rate. The main parameters that have an influence in achieving ZVS are COSS, that I told you about the output capacitor from the MOSFET, and transformer parasitics. Transformer parasitic is nothing but leakage inductance. Yeah, these are the PSW waveforms. So if you consider Q1 and Q4, they are on at the same time. So we will get this type of voltage waveform at the primary side, VAB, at the voltage primary side. And this is the secondary transformer voltage. So this is the output voltage, which is a DC, and this is a current, which has the primary current waveforms. coming to the transformer is a key element. Yeah, one more thing. As a industrial perspective, I will say till now, lot of industries, they have a problem in magnetics design and EMI filter design. Till now, we are just guessing. So from the experience we have, so I am working in R&D. So I am working with so many people who have experience in 20 to 25 years of experience. So whatever they are suggesting, like in the magnetics design, till now we don't have the what you can say that step-by-step procedure to selecting the magnetics. Like you can say that core, toroidal core or E core or transformer core. We don't have the you have to follow this process also. Then only we will come to the end that this is the core we have to get it. Till now we don't have any hard and fast rule that the same procedure we have to follow. The magnetic design is a problem in the industry perspective, and we have so many formulas, so many equations on magnetics. If we search in article also, if we search in books also, but till now no what do you say that equation or formulas, it doesn't satisfy our perspective, practical perspective. If I am getting 4 microhenry, if I am selecting for inductor, if I am applying the formula, I am getting L equal to some 4 microhenry. According to the 4 microhenry, I will come to the one conclusion that yes, this is my core. But if you ask the expert in our industry, if he has the experience, he will tell, don't go for that, it doesn't have that much capability. You have to select more than that. And if I go to more than that, so what my formula is telling, what I am searching, what I am selecting. So this is always a what we can say that Tom and Jerry problem. Like if you are doing this is just like an idea. But while you are selecting a devices, it's totally different. So even if you coming in the transformer also, that is the same thing. Transformer, you have to do the primary turns and you have to go for the secondary turns, and if it is the what you can say that tap winding, for that also if you are selecting the wire size also. So if you are selecting wire size, what is the current limit? And if it is, for example, if I have my system has 10 ampere current, as per the 10 ampere current I have to go for 6 square ampere. But they will say no, because of the noise, because of the spikes, you can't take the 6 square mm, you have to take 10 square mm. So if I am taking 10 square mm, what is my education tells? My education telling like this, because of this is a formula, this is the equation, this is the derivation I have done. But you people are telling this one. How it is possible? They will tell, by the experience you will learn. By the experience, how I will learn? By doing the projects like this, I will also come to one conclusion that, okay, if I am getting this much ampere or if I am getting this much current, I have to go for only this one. Don't ask me why, don't ask me what is the reason. So this is the experience, we will get it, then only we will do the projects like that. So these are the some drawbacks in terms of this magnetic selection and the transformer selection. So even the great authors like what we can say that Mohammed some power electronics, we have that Rashid, Mohammed Rashid also, some foreign authors also, they are like Bible in power electronics. So even if we go to that book, if I get the equation also, if I get the formula also, we are like failing to select the magnetics or wire size based on the formula and derivation. So in the PSFB, so transformer is a key element. So here, what is the importance of this transformer? So design decisions, as I said, the semiconductor selection, turns ratio, it is a like you have to think turns ratio. If I am going for 6 turns ratio, what is my losses? So if I am selecting my inductor core, what is my losses? So if I am going for LGBT, what is my losses? Because whatever our product we are preparing, so that based on the losses we are doing. If I am as per the design calculations, if I do, my losses will be more. If I do hardware, if I do practically, my losses will be more. So that is also one problem in this selection of the components. So yeah, and as I said, the transformer is the key element, and the soft switching is also it is also one of the challenges. Number of magnetics, and if we are going for any this type of topologies, magnetics is also problem. Like if you are using 3 to 4 cores, 3 to 4 magnetics, then losses will be more. Losses will be more, then efficiency will be less. So if efficiency will be less, the product